In this video, we would like to give a short introduction to the wonderful world of analytic functions of one complex variable. And there are different things that we should mention here, but first of all, let's begin with the sets over which these functions are defined. So obviously, our starting set is the set of complex numbers, but usually the kind of set on which you want to define such a function is what we call an open set. And let me, sorry, my pen is not cooperating, but let me denote a set something with something like this. So the way I would like to visualize this set is that I draw this simple closed curve, as we call it, meaning it's a nice curve that has no self-intersections. And we omit the boundary. So this is the set D. And this is what I would like to call an open set. So a subset of C is called open if for every A in D, so this notation again means belonging to, there exists an open disk centered at A and fully containing D. So what this means is that if you give me any point A in this set, I can find a little open disk centered at that point, which is fully contained in the set D, which means that in D, I have a lot of space to move around any of its points, or relatively speaking, because as you approach the boundary, that disk may have smaller and smaller radius, but still there is a certain disk and we can move around it. So that such a set is going to be called open. And we can now talk about the notion of differentiation for complex valued functions. So let D a subset of C be an open set. And A belongs to D. Then the function f. So now we have a function which is defined at, it's defined on the set D. It is going to be called differentiable at A if the limit as z approaches A of f of z minus f of A over z minus A is a complex number. Now, one might argue, well, how do we define limits for complex functions? And in general, it's pretty much the same definition. So since there is a notion of proximity, in complex numbers, so two complex numbers have a distance between them, then we expect the this quantity f of z minus f of a over z minus a to approach a complex number as z approaches a. This number will be denoted by f prime of a. Our goal here is to study functions that are differentiable at every point of their domain of definition. So we have a very nice name for these functions. If f from t to c is differentiable at every point of b, then it is called analytic or holomorphic on D. So these are the main objects of our study. So we will want to talk about functions that are analytic, meaning their derivative is defined at every point of their domain of definition, and their domain of definition happens to be an open set. So to give some examples, polynomials are analytic functions on C. In particular, the same differentiation rules that we have seen for real numbers apply to complex polynomials. So for example, let's say that you had 5z cubed plus z plus 1, then f prime of z would be 15 z squared plus 1, and so on. Then we can define interesting analytic functions by considering series. So for example, we can define the exponential function by the formula 1 plus z over 1 factorial plus z squared over 2 factorial plus z cubed over 3 factorial, and so on and so forth. And, or let me write down the comprehensive formula sum from n equals 0 to infinity of z to the n over n factorial. So this function is an analytic function that extends the usual exponential function. And of course, it satisfies Euler's formula. So it turns out that e to the ix is cosine x plus I sine x. Okay, that's a very interesting formula that we get if we restrict the variable to be ix, and we recall our formulas for the cosine function and the sine function. So to be more precise, if you take 1 plus ix over 1 factorial plus ix squared over 2 factorial, plus ix cubed over 3 factorial. Then we can separate the real summands from the complex summands, from the ones that have I in front of them. And basically what you get is something like 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. So in other words, for all even exponents, we get a real term. And for all odd exponents, we get an imaginary term. And if we factor out x, then we will get x over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on and so forth. And of course, if we remember our calculus, this is the same thing as cosine x, and this is the same thing as sine x. And that gives us this very nice formula. And actually, there is a very general principle that we're going to allude to a little later that tells us that this formula actually extends for all complex numbers. So we have e to the I z is equal to cosine z plus I sine z, where, interestingly enough, we can extend, z here, we can extend the function cosine and sine to all complex numbers, again by using their corresponding series. So cosine of z is going to be defined as 1 minus z squared over 2 factorial plus z to the 4 over 4 factorial minus, and so on. And sine of z is going to be defined as z minus z cubed over 3 factorial. I mean, you can always visualize in 1 factorial here, plus z to the 5th over 5 factorial minus z to the 7 over 7 factorial, and so on and so forth. What is interesting is that the moment we delve into analytic functions, the whole picture of power series comes in. And this is what makes analytic functions so special. So maybe one of the most important properties of such functions is the following, that if f from D to C, and here always I will think of this as an open set, is analytic, and this disk, so all Z in C such that their distance from A is less than, let's put a number delta, is a subset of D for some delta greater than 0, then there exist complex numbers C0, C1, C2, and so on, so that f of z is equal to the sum from n equals 0 to infinity of Cn times z minus a to the n. So in other words, every analytic function is an infinite polynomial on every disk contained in its domain of definition. This is huge. It tells us, for example, that every analytic function is infinitely many times differentiable. which is certainly something that's far from being true for real functions. So you can have a real function which is everywhere differentiable on the real line, and when you take its first derivative, it's not differentiable at a single point. You can never have these four complex functions. In fact, these coefficients here are none others but essentially the derivatives divided by n factorial. So in some sense, analytic functions are very rigid objects, and the moment we cross over from the real world to the complex world, there is so much difference, and the analytic functions are behaving in general in a much better way. Still, they have all sorts of secrets to explore, hence our interest in the zeta function. But that's our first encounter with these very special functions. So to recap, a function f defined on this special kind of set, which we called open set, is called analytic if it's differentiable at every point of the set in the usual sense that we had for real numbers. What is different from the case of real numbers is that the consequences of the existence of this limit for every point are enormous. And we have the very interesting fact that any such function is pretty much an infinite polynomial within every disk. And we also gave these interesting examples of analytic functions that we get by extending well-known functions of real numbers. So it's actually a very interesting question of how in the world one would go about proving something like that, proving in such generality that every analytic function is a power series over its over any disk within its domain of definition. And that's something that we will actually try to do a little later. We will try to explain how this goes. But for the moment being, we would like to just confine ourselves to defining the derivative, to seeing this very interesting property, and little by little see how all this theory applies to specifically to the zeta function. And that's all.